In this lecture, we'll look at the state pattern. To paraphrase the Gang of Four definition, this lets an object change its behavior based on its internal state. So it looks like the object is turning into a different class because its behavior has changed, even though it's not actually changing classes. The way we actually implement this pattern in practice is typically using something called finite state machines. Let's look at a couple examples. This is a finite state machine for a player in a platformer. So the circles are different states the player can be in. So they can be standing or walking or jumping or falling. And the way we move between those states is we follow one of those arrows, those edges that are called transitions. And really the way this happens in practice is the transition is caused by some event. So we transition from walking to jumping by pressing the space key. And we transition from jumping to falling when our vertical speed becomes greater than 0. The way we would implement this finite state machine is usually with a switch statement or an if, else if statement that actually says, if I'm in this state, here's how I behave. If I'm in this state, here's how I behave, and so on. That's one of the common ways that we would implement a finite state machine. Here's another example of a finite state machine, and this is a horribly stupid enemy NPC. So think of this as a 2D game because I'm talking about the number of pixels here, but it could certainly be world units in Unity as well. And that's really probably how we would implement it even in a Unity 2D game. So I'm wandering around as an enemy, and if the player gets within 200 pixels, I start chasing the player. But if I get close enough, if I get within 100 pixels, then I start running away. And after a second, I decide that I've forgotten that I was scared of the player, and I start wandering again. The point is not that this is a fantastic enemy NPC that you should implement in your RPG. It is instead another example of how we express states and remember different behaviors in each of those states. For example, when the enemy NPC is chasing the player, he's moving toward the player. And when the enemy NPC is retreating from the player, they're moving away from the player. So the behavior of the enemy depends on the state that the enemy is in. To recap, in this lecture, we saw how we can use finite state machines to implement the state pattern. And I will say that finite state machines are particularly useful when we're implementing artificial intelligence in our games.